Welcome. In the previous few videos, we looked at some general properties of second-order homogeneous linear differential equations. In this video, we're going to look at our first solution method to solve second-order homogeneous linear differential equations. This first solution method is called reduction of order. As the name implies, what we seek to do is reduce the order of the ODE by 1, going from second order to first order. We hope that this reduced order equation will be easier for us to tackle. I remind you once again of the general form of our second order linear homogeneous ODE. As a starting point for this conversation, we're going to assume that we already know one solution to the ODE, and we're going to call this solution y1. Now recall from the previous videos that for a second order homogeneous ODE, we can have at most two linearly independent solutions. Therefore, we seek the possible second independent or fundamental solution to the ODE. Now, we might be tempted to say that y2 is maybe of the form c multiplied by y1. However, recall that a constant multiple of a fundamental solution is linearly dependent and therefore is not a viable solution. We need a second linearly independent solution. So what we're going to do is propose a new solution, y, which will be equal to v multiplied by y1, where v is a function of x, which is so far unknown. So the purpose of this video is actually to figure out what this factor v is. So starting with this definition of y is equal to v multiplied by the first known solution, we're going to take its derivative. So y prime will be equal to, and again we just apply the product rule, so we're going to have v prime y1 plus v y1 prime. So again, we're dealing with a second order ODE, so we can anticipate that we might need the second derivative. So here is our second derivative. So we're going to substitute, and why don't we call this equation 2? We're going to substitute this into equation 1. So substituting 2 into 1 gives us the following expression over here. And we've done a bit of rearranging of variables. Now notice this bracketed term over here. So we notice that this is essentially our second order ODE with solution y1, which we know to be a solution to the ODE, so therefore all of this is equal to 0. So all we are left with now is this remaining term here. If we divide these remaining terms by y1, we obtain the second derivative of v, which is still unknown, plus p of x plus 2 y1 prime over y1, all of this being equal, we have a v prime over here, and that is all equal to 0. So we still have a second order ODE, but now for this unknown v prime. And it's at this point that we effectively reduce the order of our ODE. So we're going to let a new variable w equal to dv by dx. And doing this allows us to say that w prime plus p of x plus 2 y1 prime over y1 multiplied by w is equal to 0. And this is where we have reduced the order of our differential equation. Notice that this is a first order homogeneous and linear differential equation for which we know the solution. We have seen how to solve this. We can use the integrating factor method. So recall that we need to find that integrating factor, which we will call mu of x. And that will be equal to e multiplied by, and recall we, in the integrand, we include this entire term which multiplies the function, the unknown function. So we're going to have 2 y1 prime over y1 plus p of x dx. And I'll let you solve this for yourself. So perhaps consider hitting pause and try to carry out this integral yourself. So this gives us y1 squared e to the power of the integral of p of x dx. So this is our integrating factor for the solution of equation 3 over here. So recall that the general solution for a first order linear ODE using the integrating factor method is of the form w is equal to 1 over mu of x multiplied by the integral of mu of x rx dx plus c. So in equation 3, we are actually dealing with a homogeneous differential equation. Therefore, this entire term here goes to 0. So what we are left with is just c over mu of x. Now we can drop the c and just let it equal to 1. And we can deal with these constants later on in our general solution to the second order ODE. So w will be equal to 1 over mu of x, which we found to be equal to this. So this is y1 squared multiplied by e to the power of negative p of x dx. And now remember that we've said that w is just equal to dv by dx. Therefore, we can integrate this and just say that v is equal to the integral of 1 over y squared, y1 squared, multiplied by e to the negative p of x dx, and all of this multiplied by dx. And this is the unknown factor that we seek in order to find that second linearly independent solution for a second order linear homogeneous ODE, given that we already know one solution, y1. So our general solution will be y is equal to c1 y1 plus c2 and then y2, which will be equal to v multiplied by y1. where v comes from this above equation.